Hi, welcome to an electronic lesson geared towards incorporating an advanced strategy to draw Lewis structures, which is in and of itself more contemporary and versatile than the method for drawing Lewis structures that you have now. All right. If you'll take a look at this kind of curriculum map for opening of organic chemistry, give you some motivation and kind of where we are at the moment within the course, kind of 2 weeks in. I had to be fair to you to let you know what an organic compound is. So maybe your definition of an organic compound now is different than what you had conceived it starting the course. And an appreciation for how strong carbon-carbon bonds are compared to nitrogen-nitrogen bonds, compared to oxygen-oxygen bonds. And did you remember what catenation referred to? And from there, I asked you to watch, and thank you, because those were two probably 40-minute movies, adding up to 80 minutes. Watch electron configurations and atomic orbitals, that video lesson. So thank you. And I recapitulated that on that Friday. Out of that came a working knowledge of valence electrons, which are derivable. You don't have to memorize a lot of facts here. So from periodic table column headings, I've tried to sell you on the fact that you don't have to memorize as much. So you can just work the problems through. And then we had talked about octetal interpretations, how they're different for row 2 atoms and row 3 atoms. And then we went into formal charge, which was a very important topic that was homeworked, of course, as was the octetal interpretation. So we started with octetal and formal charge. And from here, it's almost like a fork in the road when you're driving. The road splits. We're going to take the fork in the road, which goes to curly arrow theory, because in order to do curly arrow theory, we want to have a fresh memory of formal charge. Okay. And from that, we will go to, maybe you've heard of it before, resonance theory. Coming into resonance theory, merging into this resonance theory is the line angle formula. So you're seeing here why organic chemistry is difficult, because if you don't understand octetal, it's that's hard enough when you try to go to curly arrow theory, and then you have another stream of knowledge, line angle theory, line angle formula going into this. So you can do it. We're taking it nice and slow. So it's just piecemeal. It's delivered to you piecemeal. And if I was to cover Lewis structures for organic chemistry, the following lecture after I covered formal charge, then I fear that when I turn back to curly arrow theory, that knowledge of formal charge is not going to be as fresh in your minds, and that would be an inhibition to your learning. And from there, you can see that the task beyond that is VSEPR, or valence shell electron pair repulsion theory. And shell is a bad word for that because shells are hollow and atomic orbitals are not hollow. Next slide in this introduction, let me just move my head. The initial method that you kind of know right now, based on previous coursework, to your credit, is kind of facing up the lone pair electrons, as for instance for carbon dioxide, and bonding them. Yeah, it works. But for organic chemistry structures, which could have triple bonds, or could have negative charges, or could have double bonds, or could have positive charges, who knows, when you get a formula like HNCO, I mean, what's going to come out of that? We have to be more versatile and fleet of foot. And this method I'll show you here, as you can see, it's sketched out a bit, is a little more open-ended, and it's orderly. It has a process, and that's what today is about. And where would this end up? For the test, this very well could be the bonus points on the test. You remember, the test is 50 points, and you get 5 points of bonus And so this very well, I would lay odds that what I'll be talking about within this movie would be the bonus problem, partial credit afforded. As you can see here, we can draw carbon dioxide a different way and arrive at the same result. And this is how students across the country, across different campuses, learn how to do Lewis structures. Hopefully they graduate with the method on the bottom of the page rather than the method on the top of the page at their ready. So we had to calculate something, a kind of a back of the envelope calculation, valence electrons, the so-called valence electron count. And we start by preferentially placing lone pair electrons on the outer peripheral atoms, not the center atom, no, on the outer peripheral atom, as you can see there. And then we generate a formal charge workup for these atoms. And there's an equivalency we can do to make bonds so long as one atom, as you'll see it soon, has a charge, a positive charge over here, and bonded to the other atom, which has both a negative charge and a lone pair. If you get 1, 2, 3, positive charge, check, negative charge, check, lone pair, check. These three things can turn into a triple bond. Excuse me, a double bond. Pardon me, I meant to say double bond. The files that we'll need, I'll speak more about that. It's called the grand equivalency. I'll say that again, the grand equivalency. The files that you'll need to access, you can hit pause on the movie right now to gather these files or print them out or something, or get a pencil and paper ready for active learning. Or I believe they're highlighted in dark blue. There's one in light blue, so looks like the screenshot wasn't too good. But the file that we'll be looking at is stepwise Lewis structures in college method. That's the file name 1.3 and 1.3 worksheet for Lewis structures with college method. Those are the two files, chapter 1, section 3. And also please get together that periodic table with the column headings, column vertical, column 1, vertical, column 2. So that periodic table will come in use. So go ahead and hit pause now while you would find those files. And then we'll get learning. Let's look at the periodic table first, okay? So let's learn how to do the calculations, right? Because they'll be part of the problems that we'll be doing for remember that contemporary, advanced, versatile method called for lack of a better word, the college method, which can better anticipate if a positive charge would end up on a structure in the final answer, or this structure has a double bond that you're surprised there's a double bond there, but yes, it's there. So the college method will better be able to anticipate that for you. Partial credit afforded, of course. All right, so I typed this out here. You can write it out. You can feel free to hit pause and write it out. So to interpret this formula, the number, see where the cursor is bouncing? The number of valence electrons is equivalent, equal sign, to however many atom A's there are in a given formula times the column number of atom A plus however many atom B's are in the formula plus the column number of atom B, whether it's fluorine or boron, and plus however many of atom type C there are and the column of atom C plus however many atoms you have. If you have 4 atoms, you'll have 4 terms. If you have 2 atoms, you'll have 2 terms, and plus any adjustment to charge. This outcome should be an even number, not odd. If you have an odd number, such as 15 or 21, that's incorrect. Something happened that we have to go back and check that. And an illustration will work nicely. So don't worry if you don't understand it yet. I'll work up the valence electron count for these examples here. Nicely. I was about to ask, do you have any questions? But I'd be asking it to myself. So the formula that we'll be calculating is for the compound H3COF. Okay, that's the compound that you're given. You're given a compound formula and you're asked to calculate quantity number. It could be 22, it could be 30, it could be 16, I don't know. The number of valence electrons in that for that formula. To do this, I'll move my head again. We have to have the column numbers. So I already put them, I typed them in there this time rather than handwriting with the mouse. Column 1, vertical column 2, vertical column 3. I hope you're following vertical column 5. So these, now we're on the periodic table now. And right now we're learning about valence electron count, this calculation. So let's give it a try. Here's the calculation here. And here's the problem. Calculate the valence electrons for H3COF. This should be an even number. Put that there and let's try it out. Okay, so you can see that there are, if I'm looking at this formula now, okay? Let's focus on this formula, everybody. All right, right. So you have taken that formula in, you can see there are how many? 3 hydrogen atoms. And hydrogen is in column what? 1, 3 times 1. And then you can see here, how many carbon atoms are there? 1. Sorry, I can't use subscripts here, but there's 1 carbon atom, and that's in column 4. Substitute in. And how many oxygen atoms are there? 1. Hopefully you get the idea. 1 oxygen atom, that's in column, vertical column 6. My cursor is waving over right now. What's this 8 here? What is that? You're confusing me. What is this 8? Oh, that's the atomic number, the number of protons oxygen has, and its nucleus is 8. So that's all that is. And there's 1 more atom, fluorine. How many? So we need an additional term, don't you know? 1 fluorine times column 7 resides in column 7. And any adjustment for charge? No, you can see that the formula here, if you will, H3COF, it's not ending with a positive charge or a negative charge. So it's net neutral. I'll say that again, it's net neutral, isn't it? So I can put here 0 if you like, or else you can just omit the term in its entirety. Oops. Yeah. Hopefully, fingers crossed, this is an even number. Fingers crossed. Seven plus 13, 20. 20 valence electrons. That means total in the molecule you would have, a bond is 2 electrons, right? Dot electrons, so bonds and dots, overall 20. Very useful information. Let's try another one. Oh, I missed it. Be right with you. Okay, next up, adding second, HFCCF. Why is it written like that? Come on. Why don't they just write HF2C2 plus? Well, why not? Why do they do that? Like, why are you making it more complicated? Well, you'll be glad they wrote it like this because they're giving away how the atoms are bonded. H is bonded to F, is bonded to C, is bonded to C, is bonded to F. So that is helpful as the problem proceeds. You may not appreciate that now when you're calculating the formula. It causes us to take more care, but that's the best hint you could ask for. So that's why that's written like that. Okay, if I can. Okay, let's see about substituting in here, shall we? How many hydrogen atoms are there, right? So we're looking at this formula. Eyes on the ball, eyes on the formula. How many hydrogen atoms are there? One hydrogen, and it's in column 1, 1 times 1. Getting to know the product table a little better based on the columns. How many carbon atoms are there? Excuse me, I think we skipped fluorine. How many fluorine F atoms are there? There are 2 fluorines, one at the beginning and one at the end, each in column 7. How many carbon atoms are there? I see CC back to back. There's 2 carbon atoms, each in row 4, excuse me, column 4, excuse me, column 4. And now we will have this adjustment for charge. Well, just like carbonate is CO3 2- from general chemistry, right? Just like ammonium is NH4+. Oops, 4+. Like that. This formula is HFCCF+. So the plus is part of the formula. I think I explained that pretty well. Remember, we're counting electrons, right? What are we counting? Are we counting pennies or dollars? No, we're counting electrons. Okay, we're counting electrons. And electron is what charge? Negative. And what charge do we have here? A positive, right? If we're counting electrons, 1, 2, 3, and we have a positive, doesn't it make sense that I'm going to subtract 1? I'm counting electrons, negative particles. I have a positive at the end. These things kind of are opposites with each other. So I'm going to say -1. So I explained that the best I could, -1. And hopefully this will break even for us. Doing it in my head now. 23, 15. I got 15 for the first 2 terms plus 8 is 23. Oh no, that's odd. Oh no. -1, it's going to be 22. So that's, I feel better about that then. So plant these over here. And finally, okay, I was worried I was not recording. Whew. And finally, I have here, I've done that before. The formula OCCH. Again, that's written for a reason. And let's take this number of hashtag valence electrons. It truly is a back of the envelope calculation. You could do this standing up on the back of an envelope. It's equal to, if you take a look at the formula, there's 1 oxygen, don't forget the brackets, 1 oxygen if I can, column 6, sorry to announce this, but if I'm getting on your nerves, plus 2 carbons, right? CC back to back. It seems like we just had that times 6. No, times 4. I beg your pardon. Sorry to worry you there. And what's the next one? Hydrogen is in column 1. There's only one of those. 1 times 1. plus any adjustment for charge, any. You may not have an adjustment for charge. For the first one we did here, there was not an adjustment for charge because H3COF was neutral, if you recall. Any adjustment for charge, and there will be. You guys are smart, so you see here that's OCCH minus. What are we counting? Negative particles. I see a negative particle. There it is. There's a minus, right? So well, we're going to add a 1. Remember what you're counting. You're counting electrons. Close bracket. Add a 1. Yeah. 8 plus 6 is 14 plus 15 plus 16. Answer here is 16. We will come back to these answers. We'll use them for future problems. Okay, you can make an index card out of that, front and back. Add that to the toolbox. You know now how to calculate with proficiency valence electron count. And that bonus problem on the test, September 29th, will be partial credit. So at least maybe you can just grab those points. Okay, so that will help. That will be good for you. And now, with your permission, I would ask for your permission before I would proceed, but I have to do this without any student feedback. So, and so now I'm going to show you a scouting report rather than doing a problem live. I've never seen this problem before. Okay, this is so I want to show you what a problem will look like. You kind of have an idea already, but I want to show you a good problem, what a problem will look like, and then we'll do a few. So this is the file 1.3. It's in the upper banner here. 1.3, chapter 1, section 3. It may not seem like we've covered a lot. I never liked that feeling where we cover so much and we're still in chapter 1, section 3. But you are, trust me, you are covering a lot. That's just how your author has put these topics into the chapter. Chapter 1, section 3, stepwise Lewis structures in the college method. That's how I named it for my notes. Okay, that's the file you want to get. So I'll give you some time to find that file. Time in. Right, so let's just cover a few odds and ends. You can see here that we're trying to find you could have done this with the so-called general chemistry method or the old method, the high school method. This problem here, AlCO3, aluminum chloride, is a nice problem for that simplistic method. It fits well. AlCO3, if you were to work that up, valence electron count is equal to 24. Aluminum is in column 3. You have 7 chlorines. Excuse me, you have 1, 2, 3 chlorines each in column 7. So 3 from the aluminum plus 21 for the chlorines, 24. There you go. I took this opportunity to present to you the fact that when you have a formula AlCO3, the atom of lower quantity, see there's only 1 aluminum against 1, 2, 3 chlorine. So aluminum is not as abundant, right? Right. So the atom of lower abundance is put central, whereas the atoms of higher abundance are put to the periphery, to the edge. Okay. And this is the process, reading from left to right, almost like you would a newspaper or anything. Calculate the valence electrons first with this. If you want to do the contemporary method, calculate the valence electrons first, then position the atoms in space, putting the outer atom or atoms peripheral, the atoms of higher abundance, correct? Correct. At the edge, and the atom of lower abundance, there's only 1 aluminum, put in the center, right? And then in sequence, we make sigma bonds to the outer atoms. Each bond is how many electrons? How many times have I asked that? I'm sorry to keep bringing that up. 2 electrons in a bond. So we make bonds to the outer atoms. There are 3 bonds. So almost like an accountant in an economics class from the economics department, you would deduct 2 electrons per bond. 24, you started with a bank account of 24, and you deduct, there are 3 bonds, hyphen, 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 with 2 electrons, 18. 18 electrons left in the bank account. And then we maximize lone pairs on outer atoms. So chlorines, if you look at this chlorine here, if I can highlight that, this is a really nice Adobe Reader program. So I highlighted that program there. What I meant to say was I highlighted that chlorine there, and you can see that this chlorine, as of the moment, if I put my face over this chlorine has its south position taken up, but it has room over here, west, it has room, sorry if you know this, north, and it has room to the east, 4 electrons. It has 3 open seats for electrons. And so that means I can put 1, 2, 3, 4, dot, 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 dot. I can put 6 electrons. Before, chlorine would meet an octet of 8 electrons. And if you count up all these dots, hope I don't make you dizzy. If you count up all these dots, they would amount to 18 dots, 9 lone pairs overall, 2 electrons in each pair, and that's what we went when it ended with 0. Okay, so that was the take-home message there. And I want to scroll ahead to the next problem. Let's take a look at the next page, and we'll be doing some of these in a moment. So calculate valence electrons, double bonds. This example will have double bonds in it. Okay, let's take a look at that. HCO2H, it's given to us. Valence electron count is 18. This is neutral. This is a neutral compound. And so if you were to line this up, since carbon makes so many bonds, I'm going to type this out because I forgot to. Since carbon makes 4 bonds, the most of any element, right? Nitrogen makes 3, oxygen makes 2. Since carbon makes 4 bonds, carbon is often in the center. So that's why carbon's inner, and the oxygen to the left, oxygen to the right. Since carbon makes so many bonds, I'm going to have carbon have 1 hydrogen, and since there's only 1, so this would you'll learn more about where to place the hydrogens over time. So kind of don't want to talk about too much, but if you'll accept for the moment, the Lewis structure skeleton is OCO, and the atoms stated are bonded to H's. Can you take that on faith for just a moment's time? Okay, thank you. The valence electron count is 18. What is that? What is that? That's this formula, right? Where is it? There it is. That's the formula there. If you work that up for HCO2H. And we will position atoms in space, make sigma bonds from the O to the C, from the C to the O, from the O to the H, and from the C to the H. I count 1 and a 2 and a 3 and a 4 bonds. Each bond is 2 electrons. We had 18 to start with. Deduct, almost like a bank account, 18 minus 4 times 2 is 8, 10 left over. This is important now. This is important. Please listen carefully. Please listen carefully. Look at this preferential treatment. Oh, the electrons on the outer atoms preferentially. But what about that carbon? How come that carbon doesn't get any lone pair? This isn't fair because carbon's in the middle. With this method, we want to preferentially place lone pairs of electrons on the outer atoms. Okay? Okay. And then we can calculate or deduce formal charges. We talked about this on Friday. For reasons stated on Friday, this oxygen has a negative charge. This carbon has a positive charge. Little hint, How many bonds is this carbon making? Take a look at the blue fishing line, that carbon I'm pointing to as one bond to the left, one bond to the right, one bond down, 3 bonds. Carbon should make 4 bonds. Carbon has less bonds. Electrons are in bonds, less bonds, less negative, positive. And at the bottom, this is something called the grand equivalency. If you have a bond, listen carefully, please. So I just ended an important point about preferentially putting lone pair electrons toward the periphery, toward the edge, okay? Toward the edge, toward the outer atoms, whatever they are. In this case, it was 2 oxygens. Another important point, the grand equivalency. If you have a bond, everybody, and you have on one side of the bond an atom with a positive charge, and on the other side of the bond, you have an atom with a negative charge and a lone pair. These 3 things, check out, check out, check out. Positive charge one side, negative charge the other side, lone pair on that same side. You can mix this and cash it in. You can trade it in for a triple bond, almost like at a pawn shop. You can cash in a positive charge on one atom in conjunction with the negative charge on the other atom and a lone pair on that same atom. 1, 2, 3, even exchange, this becomes a bond. That's called the grand equivalency. And that's what happened above. I took this. I took this. I took this. And it became this bond. Maybe in looking at this, you didn't expect a double bond to form there, but it did. And let's verify the valence electron count is correct, shall we? Two, 4. Hopefully we have 18 electrons. 6 for the bond from carbon to hydrogen. 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. That wasn't the best presentation, so let me try that again. I'll go from left to right, okay? Counting the electrons, this should add up to 18, should it not? 1 dot, 2 dot, 3 dot, 4 dot, bond 5, 6, bond 7, 8, bond 9, 10, bond 11, 12, bond 13, 14, 15, 16, 17, 18. It's 18 electrons.